Machine Learning Using R, with time series and industry-based use cases in R. Second edition. Karthik Ramasubramanian Abhishek Singh. Introduction. In the second edition of Machine Learning Using R, we added a new chapter on time series modeling, Chapter 9, a traditional topic that has its genesis from statistics. The second newly added chapter is Deep Learning, Chapter 11, which is fast emerging as a subfield of machine learning. Apart from these two new chapters, the overall presentation of text and code in the book is put out in a new reader-friendly format. The new edition continues to focus on building the use cases using R, a popular statistical programming language. For topics like deep learning, it might be advised to adopt Python with frameworks like TensorFlow. However, in this new edition, we will show you how to use the R programming language with TensorFlow, hence avoiding the effort of learning Python if you are only comfortable with R. Like in the first edition, we have kept the fine balance of theory and application of machine learning through various real-world use cases, which give the readers a truly comprehensive collection of topics in machine learning in one volume. What you'll learn. Understand machine learning algorithms using R, master a machine learning model building a process flow, theoretical foundations of machine learning algorithms, industry-focused real-world use cases, time series modeling in R, deep learning using Keras and TensorFlow in R. Who this book is for. This book is for data scientists, data science professionals, and researchers in academia who want to understand the nuances of machine learning approaches/algorithms in practice using R. The book will also benefit readers who want to understand the technology behind implementing a scalable machine learning model using Apache Hadoop, Hive, Pig, and Spark. This book is a comprehensive guide for anybody who wants to understand the machine learning model building process from end to end, including practical demonstration of concepts in R, machine learning models using Apache Hadoop and Spark, time series analysis, introduction to deep learning models using Keras and TensorFlow using R. Introduction. Chapter 1. Introduction to Machine Learning and R. Beginners to machine learning are often confused by the plethora of algorithms and techniques being taught in subjects like statistical learning, data mining, artificial intelligence, soft computing, and data science. It's natural to wonder how these subjects are different from one another and which is the best for solving real-world problems. There is substantial overlap in these subjects, and it's hard to draw a clear Venn diagram explaining the differences. Primarily, the foundation for these subjects is derived from probability and statistics. However, many statisticians probably won't agree with machine learning giving life to statistics, giving rise to the never-ending chicken and egg conundrum kind of discussions. Fundamentally, without spending much effort in understanding the pros and cons of this discussion, it's wise to believe that the power of statistics needed a pipeline to flow across different industries with some challenging problems to be solved, and machine learning simply established that high-speed and frictionless pipeline. The other subjects that evolved from statistics and machine learning are simply trying to broaden the scope of these two subjects and putting it into a bigger banner. Except for statistical learning, which is generally offered by mathematics or statistics departments in the majority of the universities across the globe, the rest of these subjects like machine learning, data mining, artificial intelligence, and soft computing are taught by computer science department. In the recent years, this separation is disappearing, but the collaboration between the two departments is still not complete. Programmers are intimidated by the complex theorems and proofs, and statisticians hate talking, read as coding, to machines all the time. But as more industries are becoming data and product-driven, the need for getting the two departments to speak a common language is strongly emphasized. Roles in industry are suitably revamped to create openings like machine learning engineers, data engineers, and data scientists into a broad group being called the data science team. 2. The purpose of this chapter is to take one step back and demystify the terminologies as we travel through the history of machine learning and emphasize that putting the ideas from statistics and machine learning into practice by broadening the scope is critical. At the same time, we elaborate on the importance of learning the fundamentals of machine learning with an approach inspired by the contemporary techniques from data science. We have simplified all the mathematics to as much extent as possible without compromising the fundamentals and core part of the subject. The right balance of statistics and computer science is always required for understanding machine learning, and we have made every effort for our readers to appreciate the elegance of mathematics, which at times is perceived by many to be hard and full of convoluted definitions, theories, and formulas. 1.1 Understanding the evolution. The first challenge anybody finds when starting to understand how to build intelligent machines is how to mimic human behavior in many ways, or, to put it even more appropriately, how to do things even better and more efficiently than humans. Some examples of these things performed by machines are identifying spam emails, predicting customer churn, classifying documents into respective categories, playing chess, participating in Jeopardy, cleaning house, playing football, and much more. Carefully looking at these examples will reveal that humans haven't perfected these tasks to date and rely heavily on machines to help them. So now the question remains, where do you start learning to build such intelligent machines? Often, depending on which task you want to take up, experts will point you to machine learning, artificial intelligence, AI, or many such subjects that sound different by name but are intrinsically connected. In this chapter, we have taken up the task to knit together this evolution and finally put forth the point that machine learning, which is the first block in this evolution, is where you should fundamentally start to later delve deeper into other subjects. 1.1.1 Statistical Learning. The white paper, Discovery with Data, Leveraging Statistics with Computer Science to Transform Science and Society by American Statistical Association, ASA, 1, published in July 2014, defines statistics as the science of learning from data and of measuring, controlling, and communicating uncertainty is the most mature of the data sciences. This discipline has been an essential part of the social, natural, biomedical, and physical sciences, engineering, and business analytics, among others. Statistical thinking not only helps make scientific discoveries, but it quantifies the reliability, reproducibility, and general natural, biomedical, and physical sciences, engineering, and business analytics, among others. Statistical thinking not only helps make scientific discoveries, but it quantifies the reliability, reproducibility, and general uncertainty associated with these discoveries. This excerpt from the white paper is very precise and powerful in describing the importance of statistics in data analysis. Tom Mitchell, in his article, The Discipline of Machine Learning, 2, appropriately points out, over the past 50 years, The study of machine learning has grown from the efforts of a handful of computer engineers exploring whether computers could learn to play games, and a field of statistics that largely ignored computational considerations, to a broad discipline that has produced fundamental statistical computational theories of learning processes. This learning process has found its application in a variety of tasks for commercial and profitable systems like computer vision, robotics, speech recognition, and many more. At large, it's when statistics and computational theories are fused together that machine learning emerges as a new discipline. 1.1.2 Machine Learning, ML. The Samuel Checkers playing program, which is known to be the first computer program that could learn, was developed in 1959 by Arthur Lee Samuel, one of the fathers of machine learning. Followed by Samuel Richard S. Mihalski, also deemed a father of machine learning, came out with a system for recognizing handwritten alphanumeric characters, working along with Jacek Karpinski in 1962 to 1970. The subject from then has evolved with many facets and led the way for various applications impacting businesses and society for the good. Tom Mitchell defined the fundamental question machine learning seeks to answer as, how can we build computer systems that automatically improve with experience? And what are the fundamental laws that govern all learning processes? He further explains that the defining question of computer science is, how can we build machines that solve problems, and which problems are inherently tractable/intractable, whereas statistics focus on answering what can be inferred from data plus a set of modeling assumptions, with what reliability? This set of questions clearly shows the difference between statistics and machine learning. As mentioned earlier in the chapter, it might not even be necessary to deal with the chicken and egg conundrum, as we clearly see that one simply complements the other and is paving the path for the future. As we dive deep into the concepts of statistics and machine learning, you will see the differences clearly emerging or at times completely disappearing. Another line of thought in the paper Statistical Modeling, The Two Cultures by Leo Breiman in 2001-3, argued that statisticians rely too heavily on data modeling, and that machine learning techniques are instead focusing on the predictive accuracy of models. 1.1.3 Artificial Intelligence, AI. The AI world from very beginning was intrigued by games. Whether it be checkers, chess, Jeopardy, or the recently very popular Go, the AI world strives to build machines that can play against humans to beat them in these games, and it has received much accolades for the same. IBM's Watson beat the two best players of Jeopardy, a quiz game show wherein participants compete to come out with their responses as a phrase in the form of questions to some general knowledge clues in the form of answers. Considering the complexity in analyzing natural language phrases in these answers, it was considered to be very hard for machines to compete with humans. A high-level architecture of IBM's Deep QA used in Watson looks something like in Figure 1.1. AI also sits at the core of robotics. The 1971 Turing Award winner, John McCarthy, a well-known American computer scientist, was believed to have coined this term, and in his article titled, "What is Artificial Intelligence?" he defined it as the science and engineering of making intelligent machines for. So, if you relate back to what we said about machine learning, we instantly sense a connection between the two, but AI goes the extra mile to congregate a number of sciences and professions, including linguistics, philosophy, psychology, neuroscience, mathematics, and computer science, as well as other specialized fields such as artificial psychology. It should also be pointed out that machine learning is often considered to be a subset of AI. 1.1.4 Data mining. Knowledge discovery and data mining, KDD, a premier forum for data mining, states its goal to be advancement, education, and adoption of this science for knowledge discovery and data mining. Data mining, like ML and AI, has emerged as an interdisciplinary subfield of computer science, and for this reason, KDD commonly projects data mining methods as the intersection of AI, ML, statistics, and database systems. Data mining techniques were integrated into many database systems and business intelligence tools when adoption of analytic services were starting to explode in many industries. The research paper, Weka Experiences with a Java Open Source Project 5, Weka is one of the widely adapted tools for doing research and projects using data mining, published in the Journal of Machine Learning Research, talked about how the classic book, Data Mining, Practical Machine Learning Tools and Techniques with Java 6, was originally named just Practical Machine Learning, and the term data mining was only added for marketing reasons. Frank and Mark A. Hall, who wrote this research paper, are the two co-authors of the book, so we have a strong rationale to believe this reason for the name change. Once again, we see fundamentally ML being at the core of data mining. 1.1.5 Data Science. It's not wrong to call data science a big umbrella that brought everything with the potential to show insight from data and build intelligent systems inside it. In the book, Data Science for Business 7, Foster Provost and Tom Fawcett introduce the notion of viewing data and data science capability as a strategic asset, which will help businesses think explicitly about the extent to which one should invest in them. In a way, data science has emphasized the importance of data more than the algorithms of learning. It has established a well-defined process flow that says, first think about doing descriptive data analysis, and then later start to think about modeling. As a result of this, businesses have started to adopt this new methodology because they were able to relate to it. Another incredible change data science has brought is around creating the synergies between various departments within a company. Every department has its own subject matter experts, and data science teams have started to build their expertise in using data as a common language to communicate. This paradigm shift has witnessed the emergence of data-driven growth and many data products. Data science has given us a framework which aims to create a conglomerate of skill sets, tools, and technologies. Drew Conway, the famous American data scientist who is known for his Venn diagram definition of data science, as shown in Figure 1.2, has very rightly placed machine learning in the intersection of hacking skills and math and statistics knowledge. We strongly believe the fundamentals of these different fields of study are all derived from statistics and machine learning, but different flavors, for reasons justifiable in its own context, were given to it, which help the subject be molded into various systems and areas of research. This book will help trim down the number of different terminologies being used to describe the same set of algorithms and tools. It will present a simple-to-understand and coherent approach, the algorithms in machine learning, and its practical use with R, wherever it's appropriate. We will emphasize the need to go outside the scope of this book and guide our readers with the relevant materials. By doing so, we are re-emphasizing the need for mastering traditional approaches in machine learning and, at the same time, staying abreast with the latest development in tools and technologies in this space. Our design of topics in this book are strongly influenced by data science framework, but instead of wandering through the vast pool of tools and techniques you would find in the world of data science, we have kept our focus strictly on teaching practical ways of applying machine learning algorithms with R. The rest of this chapter is organized to help readers understand the elements of probability and statistics and programming skills in R. Both of these will form the foundations for understanding and putting machine learning into practical use. The chapter ends with a discussion of technologies that apply ML to a real-world problem. Also, a generic machine learning process flow will be presented showing how to connect the dots, starting from a given problem statement to deploying ML models to working with real-world systems. 1.2 Probability and Statistics. Common sense and gut instincts play a key role for policymakers, leaders, and entrepreneurs in building nations and large enterprises. The question is, how do we change some intractable qualitative decision making into objectively understood quantitative decision making? That's where probability and statistics come in. Much of statistics is focused on analyzing existing data and drawing suitable conclusions using probability models. Though it's very common to use probabilities in many statistical modeling, we feel it's important to identify the different questions probability and statistics help us answer. An example from the book, Learning Statistics with R, a tutorial for psychology students and other beginners by Daniel Navarro, 8, University of Adelaide, helps us understand it much better. Consider these two pairs of questions. 1. What are the chances of a fair coin coming up heads 10 times in a row? 2. If my friend flips a coin 10 times and gets 10 heads, is she playing a trick on me? And 1. How likely it is that 5 cards drawn from a perfectly shuffled deck will all be hearts? 2. If 5 cards off the top of the deck are all hearts, how likely is it that the deck was shuffled? In case of the coin toss, the first question could be answered if we know the coin is fair. There's a 50% chance that any individual coin flip will come up heads. In probability notation, P heads equals 0.5. So our probability is P heads 10 times in a row equals 0.0009765625. Since all the 10 coin tosses are independent of each other, we can simply compute 0.5, 10 to arrive at this value. The probability value 0.0009765625 quantifies the chances of a fair coin coming up heads 10 times in a row. On the other side, such a small probability would mean the occurrence of the event, heads 10 times in a row, is very rare, which helps to infer that my friend is playing some trick on me when she got all heads. Think about this: does tossing a coin 10 times give you strong evidence for doubting your friend? Maybe no. You may ask her to repeat the process several times. The more the data we generate, the better will be the inference. The second set of questions has the same thought process, but is applied to a different problem. We encourage you to perform the calculations yourself to answer the question. So, fundamentally, probability could be used as a tool in statistics to help us answer many such real-world questions using a model. We will explore some basics of both these worlds, and it will become evident that both converge at a point where it's hard to observe many differences between the two.